Namaste everyone. Welcome to our next class in magnetic effects of current. As you see on your screens, these are going to be our objectives for today. We are moving in to study a new force that's called Lorentz force. And this force comes into effect when a current carrying conductor is going to be placed in a magnetic field, or when a moving charge is going to be sent into a magnetic field. Then that is when it is going to experience a force. We are going to study about that in detail. And now that we are going to come into physical quantities that are vectors, we have to know about the rules that are going to help us in determining the direction of the resultant vector. So we are going to recall Fleming's left-hand rule, which you have already done in your lower classes. And a simplified form of Fleming's left-hand rule is right-hand palm rule. We will have a look at that also. It's one and the same direction that you are going to determine, but only thing is you are going to use your right hand to determine that's these two rules are something like your Ampere's swimming rule and your thumb rule. Like, both of them are used in the same instance to find out the direction of the magnetic field, and both will give you the same answer. Similarly, these two, and using that we are going to see what happens when two parallel conductors are going to carry current in the same direction. So outcomes are also on the board. I would like you to achieve these. Hope we will achieve that by the end of this lecture. So let's move on with the Lorentz force. So suppose if there is a charge Q, let us assume, moving with a velocity V in an external magnetic field B. So let's assume that there is a charge Q that is going to be moving in a external magnetic field B with a velocity V. Then the charge is going to experience a force F. Force being a vector quantity, it is going to experience a force F that is going to be given by the magnitude of the charge into V cross B. The force is going to be dependent on the magnitude of the charge. It is going to be dependent on the velocity and the strength of the magnetic field in which it is moving. So F becomes Q times V cross B. And this is, I'm going to put a B over here because this force is what we are going to call as magnetic Lorentz force. Magnetic Lorentz force, which is F given by Q times V cross B. So if I'm going to write the magnitude of this force, we know that A cross B ka magnitude is AB cos theta. So this becomes Q V B, sorry, it is not cos theta, it is sin theta, slip of a tongue, I'm very sorry about that. A cross B ka magnitude hai AB sin theta. So the magnitude of the force FB is going to be given by QVB sin theta. And we always know that the cross product, the vector which is a cross product of two vectors, is always perpendicular to the individual vectors, and hence the Lorentz force is always perpendicular to the plane containing V and B. And what are we going to do? The direction is what is going to be determined by Fleming's left-hand rule. Now, what is Fleming's left-hand rule? You know it. If the first three fingers of your left hand are going to be mutually perpendicular to each other, then in such a way, say for example, this is my forefinger, and this is going to be my, the center finger, and this is going to be my thumb. So left-hand rule says that if the forefinger points the direction of the field, F for field, and C for current, if the center finger shows the direction of the current, that is how you would have remembered. And the thumb, M shows the direction of the motion of the conductor, that is the force that is experienced by the conductor or the charge. We also say it in a different way. We call it as F, B, I. Now that you know B stands for magnetic field, so we can call this, to remember it, as FBI, F for force, B for field, I for current. So mutually perpendicular directions, please let's get that very clearly. They are to be mutually perpendicular to each other. So if they are mutually perpendicular to each other, with the forefinger showing the direction of the field, the center finger the direction of the current, then the thumb shows the direction of the motion of the conductor. Is that clear? Right. Now, if we are going to talk about the other rule that I had put up in, the learning objectives, if we are going to look at that particular rule, that is our right hand palm rule. Now in that, why are we moving into right hand palm rule? Why at all should we move into this palm rule? Is because in the right hand you can have every rule that you're going to use in magnetism in order to determine the direction. You have right hand thumb rule, you have right hand grip rule, and you have your right hand palm rule. Wherever you need, it is only this hand, right, your right hand, that is going to be used to determine the direction of any vector quantity that you are having as a resultant in your problem. Now what does this palm rule state? Now in this palm rule, if the tip of your fingers are going to show the direction of your field, of the external field, that is the tip of your four fingers are going to show the direction of B, and your thumb is going to show the direction of the current. The thumb is going to show the direction of the current. Then the palm, the direction in which your palm is facing, is going to show the direction of the force that is going to be acting on the charge or the conductor. So current is basically nothing but the direction in which the charge is moving, right? Positive charges are moving. So palm rule states that if you are going to hold your right hand in, open up your right hand palm and hold it in such a way that the thumb is going to show the direction of the current, and the tip of your remaining four fingers, tips of your remaining four fingers are going to show the direction of the field, then the palm is going to show the direction of the force that is going to be acting on the charge or the conductor. Now let's look at F is equal to Q into B cross B, and let's look at a few special cases in which we are going to have either maximum force or zero force. So what is going to be the first case that I'm going to talk about? I hope you all know. The first case is going to be if V and B are parallel or anti-parallel to each other. That is, if the charge is going to move in the direction of the magnetic field or in a direction opposite to that of the magnetic field. In which case, what's going to happen, children? Theta either becomes 0 if it is parallel, and theta becomes equal to 180 degree if it is going to be anti-parallel. So in both the cases, we know that sine is going to, the trigonometric ratio sine is going to become equal to 0, and hence F becomes equal to 0. So when a charge is going to move parallel or anti-parallel to the applied magnetic field or the external magnetic field, it is not going to experience any force. Rather, it is going to go undeviated. It is going to go undeflected from its path without being affected by the external magnetic field. Now we are going to look at case 2, where we are going to say that if V and B are perpendicular to each other, that means my charge, the charge that you have taken into consideration is moving perpendicular, moving at theta equal to 90 degree. Perpendicular theta is equal to 90 degree, and we know that the trigonometric ratio sine is maximum for theta is equal to 90 degree. So the current, the charge that is moving in that magnetic field will experience a maximum force that is going to be given by QVB. We are writing the magnitude of the force. Remember, that is going to be maximum, that is QVB. Then we look at case 3. Now, what is going to happen when it is going to be 270 degree? That if it is going to be moving in a direction where theta becomes equal to 270 degree, if V and B are still perpendicular, but in the opposite direction, right? They are 270, they are inclined at an angle 270 degree. So what is going to happen? We know that sine of 270, it is -1. So when theta is equal to 270 degree, then it becomes equal to, the F becomes equal to minus QVB. Please understand, I'm not going to write this as minimum. This is also maximum. Please get that. You know that by now. You should know this because it's a vector quantity. The negative is not going to show that it is less. Negative only shows that it is in the opposite direction. So this will be maximum in the opposite direction. So let's get that very clearly. When this V, I'm going to put that as case 4, but let us get that Lorentz force comes into picture only for a moving charge. So that means this force does not exist when the charge is at rest, because as you put this quantity V is equal to 0, my F also becomes equal to 0. So the moment the charge comes to rest, Lorentz force ceases to exist and the charge does not experience any force in the external magnetic field to which it is subjected to. Now, we know that current in a conductor is nothing but moving charges. So obviously, if we are going to consider a current carrying conductor that is going to be placed in an external magnetic field. So I'm going to consider a current carrying conductor of area of cross section A. I'm going to consider this having an area of cross section A, and let us assume that the length of this conductor is L, and this conductor is going to be placed in an external magnetic field, and this is going to carry current in this direction. Let's assume that current is going to move in this direction. Please understand, conventional current is opposite to the direction of the flow of electrons. So the moving charges in this conductor is electron, which is going to move in a direction opposite to the direction of the conventional current. So let's analyze such a situation and see what's going to happen when such a conductor is placed in this particular magnetic field. It's a conductor, it's a solid material, and charges are going to flow through the conductor. Charges are present in the volume of the conductor. So what are we going to consider here? We are going to consider N is equal to N upon V. Now, what is this N here? Please understand, this is not turn density, which we saw in a solenoid or a toroid. This is charge density of the conductor under consideration, which is number of charges per unit volume. If we remember, we also insisted upon the difference between this N and the other turn density when we did solenoid 2. So here, the small n that we are going to use is charge density of the conductor, which is number of charges per unit volume. Good children, so let's go into our consideration over here. So what's going to happen? My F, the force that is going to act on a single charge that is going to move. Let's consider Lorentz force is for a single charge, and the charge under consideration over here is an electron. So we are going to replace Q by minus E, and I am going to replace the velocity to be drift velocity. You know that electrons are going to move with a velocity V inside. So each electron, though it is average, the average velocity of each electron is given by Vd. Now this is due to one electron. How many such electrons are going to flow through this particular conductor, for which what we are going to do is we are going to consider a small length of the conductor dl. I'm going to consider a small length of a conductor dl, and we are going to see what's going to be the force experienced by this small length of a conductor when placed in an external magnetic field. So the force is also going to become df. And what is going to be the number of electrons that are going to flow through this small length? That is capital N over here. Capital N can be written as N times V, where V becomes the volume of the conductor. So what's going to be the volume of this small cross section? Volume is nothing but base area into length. So how am I going to write this? I'm going to write it as minus number of electrons times the charge on the electron. So what is going to be the number of electrons? The charge density into the volume is going to be base area into length times the charge on each of it into Vd upon, Vd times B, right? Now, what is velocity of electron in that particular what is that given length of the conductor? The given length is dl. So how are we going to write that? We are going to write it as, it's a vector. Please understand, it's a vector. How are we going to write that vector? We are going to write that vector dl Vd vector as dl vector by dt, the rate of change of the displacement. But please get that very clearly. We did this when we studied about current element. We said that current element may dl is taken in the direction of the current, and we know Vd is going to be in a direction opposite to that of the current. So I am going to be forced to put a negative sign because my velocity is going to be, the drift velocity of the electrons is in a direction opposite to that of the line element, opposite to that of the current that is taken into consideration. So what have we written for df over here? If we are going to substitute for Vd, what am I going to end up getting df as? Df is going to be equal to minus n a dl into E, within brackets, in the place of Vd, we are going to write dl by dt cross B. Hope you got this. Now, this minus cancels off with this minus, and this being a scalar quantity, dt, is going to come out. I'm going to club it with this dl. So dl by dt, where dl and dt here are scalar quantities that we have taken, because the dl that we have considered over here was considered for volume, which is a scalar quantity. So dl by dt, which is going to give me v, the magnitude of the velocity. So I'm going to write it as n a e v d times dl cross b. Beautiful. Now what is this? NAEVD. Remember from what we did in our current electricity lesson for a relationship between current and drift velocity. Hope you remembered it. That's nothing but the current that is flowing through the conductor. So I have this to be equal to I times dl cross B. Right, children? This is the force due to the small element dl. So what are we going to do now? You know that, you already have that answer in your minds. In order that I find out the total current, that is, the total force acting on the conductor due to the external magnetic field, we are simply going to integrate df. Integral of df is going to give me F, the Lorentz force, magnetic Lorentz force. So that's going to be FB. The magnetic Lorentz force is going to be, I know I, the current flowing through the conductor is a constant current that we have considered. So this is simply integral dl cross B. Again, B is a uniform magnetic field that we have applied. So this becomes actually L cross B, because the integral goes only on the total length of the conductor. So F, the magnetic Lorentz force, is also given as I times L cross B. If it is going to be a current carrying conductor, if it is a single charge, then we wrote it as Q times V cross B. If it is a current carrying conductor, we are writing it as I times L cross B. So this is a vector. Let's not forget that this is a vector over all through over here. So magnitude of the force F is going to be given by BIL sine theta, where theta becomes the angle between the line element and the field under consideration. So F is equal to BIL sine theta becomes the force that is going to be experienced by a current carrying conductor placed in a magnetic field. And this, again, the direction of this force is going to be found either using your Fleming's left hand rule or using your right hand palm rule. Hope Lorentz force is very clear. Now we are going to consider two parallel conductors. So let's consider two long parallel conductors that are going to carry current. So I'm going to consider this as wire 1 and I'm going to consider this as wire 2. Let's consider wire 1 carrying a current I1 and wire 2 carrying a current I2, both in the same direction. We are going to find out what is going to be the effect of placing two parallel conductors closer, carrying current in the same direction next to each other. What's going to be the effect of this on the conductors that is going to carry current? So we are considering infinitely long, straight, parallel conductors that are going to carry current, right? And this current carrying conductor, we know that every current carrying conductor has a magnetic field around itself. So let's look at the magnetic field of wire 1. What will be the nature of the magnetic field? We are going to use right hand thumb rule. I want you all to hold this imaginary conductor with your right hand, thumb facing upwards, so you know that we have the magnetic field that is going to be going with respect to the first wire. If I'm going to consider a point P over here, it is going into the plane of the paper, so I'm going to put an into mark over here and I'm going to write it as B1. Whichever point I'm going to consider in between the conductors, whichever point I'm going to consider in between the conductors, the field is going to be into the plane of the paper with respect to current I1. Now this current I1, which is going to flow through the first wire, is causing this magnetic field B1, which is going to be into the plane of your screens. Now this B1 becomes the external magnetic field for the wire W2. That's going to carry a current I2. Now, what can we write about B1 when I'm going to write the magnitude of this either using Ampere's circuit law or by using Biot-Savart law? We know that the field due to an infinitely long conductor with current flowing through it is going to be given by mu naught by 4 pi 2I by, so let us consider that the normal distance is R over here. So this is going to be R. Correct? This is by applying Biot-Savart law. We know that B1 is going to be mu naught by 4 pi 2 I1 by R, because the magnetic field is produced by this current I1 that is flowing through the wire 1. Now, what did we say? This field becomes the external field for the current carrying conductor I2. So by Lorentz force, the force experienced by the second wire is going to be given by the magnitude of the external field into the current that is flowing through the wire into the length of the wire. Let us assume that the length of both the wires are going to be equal to L. So F2 becomes equal to B1 into I2 into L, because the second wire के लिए external magnetic field है B1 and second wire के लिए current है I2. So what are we going to write B1 as? B1 is nothing but mu naught by 4 pi. So if I'm going to multiply it by I2, it becomes 2 I1 I2 by R times L. This becomes the force that is going to be experienced by the second wire. What if I want to find out force experienced per unit length of the wire? Then the force due to the per unit length will be F2 upon L. This L gets divided by this F2. So the force per unit length on the wire is going to be given by F2. So let me consider this as F2 dash. So I'm going to write F2 over here. What is this F2? F2 is going to be the force experienced per unit length of the second wire. Right? Now let's look at the current that is flowing through wire 2. And let us look at the same point or any point in the same region. So let me consider such a point. Now, with respect to the second wire, if you are going to use your right hand thumb rule, then you can see that at that point, the field is coming out So I'm going to make it into a dot and write it as B2, where what is B2? B2 is the field that is going to be the resultant of the current that is flowing through W2. Now, how can I write B2? Again, we are going to apply Biot-Savart law. B2 is also going to be equal to mu naught by 4 pi, but the current that is flowing through the wire 2 is I2. So let us assume, if I have considered the point at the same distance, normal distance from the wire as we considered for the first wire, it becomes 2I2 by R. Now what is going to be, this field becomes external magnetic field. This field over here becomes the external magnetic field for the first wire. So by Lorentz force, I can write the force experienced to be equal to B2 times I1 times L. So the force per unit length experienced by the first wire is going to be, if you look at what we are going to write here, you are seeing that the magnitude is going to be the same. Isn't it, children? Are we not getting the same magnitude? Look at F1 mu naught by 4 pi 2 I1 I2 by R. F2 is mu naught by 4 pi 2 I1 I2 by R. The magnitudes of these two forces are equal. Now, what are we going to do? Being a vector quantity, we need to determine the direction in which this force is acting. So let's look at the first wire. In the first wire, current is moving up and the magnetic field is into the plane of the paper with respect to the first wire, and this magnetic field is affecting the second wire. So let's look at F2. F2 के लिए field है B1, which is out of, into the plane of the paper. Current is I2. So look at, so your hand has to be in F2, that is the second wire. With respect to the second wire, I'm going to use right hand palm rule, which is much simpler rather than spreading my first 3 fingers of the left hand. Let us also try together, children. Lift up your right hand. The tip of your 4 fingers has to point into your screen. Your thumb has to point upward. So see where your palm is facing, children. Your palm is facing to your left. That means my second wire is going to experience a force towards the left. So F2 per unit length is going to be in this direction. Wasn't that easy rather than spreading your 3 fingers? Now let's come to F1. With respect to F1, the field is B2 and the current is I1. So with respect to F1, that is the force experienced by the first wire, the field is B2. That means the fingers have to point towards you. That means you have to hold your right hand in such a way that the tip of your 4 fingers are going to face yourself, while the thumb is still facing up. And do you see where your palm is facing now, children? Your palm is facing to your right. So that means my force is going to be towards the right. So do you see, children? These two conductors are going to be subjected to 2 forces that are parallel, that are equal in magnitude, but they are opposite in direction. So what are we going to conclude? We are going to conclude that 2 parallel conductors carrying current in the same direction are going to attract each other. So what you can do is try and determine what will be the direction of the forces when these parallel conductors are going to carry current in the opposite direction. So you will not be surprised to see that if they are going to carry current in the opposite direction, they are going to repel each other. Now, one beautiful thing that practically we see about this particular analyzing that we have done now is, in a solenoid, when current is going to flow through a solenoid, it is seen that the solenoid contracts in length. That is, the wires come closer to each other. That's because every turn on the solenoid is basically parallel to each other, and we know that current is going to flow in the same direction when it is going to thread through the loops. So these currents that are going to flow in the same direction are going to experience forces that are going to attract each other, and hence the solenoid contracts when current is going to flow. Not to a greater extent, but to a certain extent it is going to contract. And that's about analyzing current that is flowing through two straight conductors, either in the same direction or in the opposite direction. So that we are at the end of our session, and we have achieved, we should have achieved, I should not say we have, we should have achieved the outcomes by now. You should be at ease to use either your Fleming's left hand rule or right hand palm rule in order to determine the force on a current carrying conductor. And if you are not very clear, replay and watch the video. You should be more at ease to determine what is going to be the effect of an external magnetic field on a current carrying conductor. I will be seeing you next live on Tuesday for the next part of our lesson, which will be studying about torque on a current carrying coil, rectangular coil in a placed in a magnetic field. Till then, stay safe.